Hello everybody, this is a video now on statistics and mechanics. We're on chapter 7, so I'm calling this 7.1. I'm going to introduce you to this idea of hypothesis testing. Okay, so this might be a lot to get your head around, but you have to believe me, with perseverance, the idea is actually relatively simple, but it's going to be very explanation heavy at first in this video. But if you bear with me as we run through these explanations of the different definitions, I'm hoping that you will eventually sort of see that the idea does make sense and it's almost intuitive. But before we do this, as ever, I have a few warm-up questions for you, which I've got here. So pause the video, jot them down, or if you're lucky enough to have a printer, get them printed off and try them. Once you've completed them, press play and hear me out when I talk through these solutions. So here we go now, I'm going to talk through these solutions with you. So warm-up question 1. We need to find the value of k for this probability distribution. So this just goes back to essentially GCSE. So the sum of all probabilities must add up to 1. So here, heads plus tails is 3k plus 5k, therefore 5k must equal 1. And if 5k equals 1, therefore if we divide through by 5, k must be 1/5. Part B, if a coin is tossed 30 times, we need to find the expected number of heads from 30 trials. Now again, probability, it's nothing definite, but all we can do is make an estimation. So using this, expected number of heads from 30 trials, well the probability now of a head, we know is 3k, and now we know that k is 1/5, 3k is 3/5. And so this tells us that, on average, we'd expect 3/5 of the flips to end up as a head. So the expected number of heads from 30 trials must be 3/5 of 30, which with a calculator or otherwise, that'll come out as being 18. So we'd expect about 18 heads. Warm-up question 2. We've got this local politician believing she has the support of 40% of her constituents. So part A, given her constituency has a population of 72,000, how many residents would she expect to support her? Well, quite obviously, this is going to be 40% of 72,000. I'm not saying it's going to be exactly that, but that's our best estimate, 40% of 72,000. So using the calculator, or if you want to do it in your head, you can do. I wouldn't advise it, to be honest. I'd advise you, if possible, to do almost everything in your calculator. So 40%, 0.40 of 72,000, that comes out as being 28,800. Now, for part B, how could you find out this information? Well, I'm going to type this actually so my handwriting's not going to get ugly and in the way in terms of being hard to read. Well, what she could do is she could conduct a survey. She can conduct a survey, or a questionnaire in fact, of these constituents, for these constituents. So it could be a survey or questionnaire, and she could ask, using this survey, a random sample of constituents. It's important that it needs to be randomized, needs to be fair. She could ask them about if they support her or not. So obviously, the bigger the sample size, the better. That needs to be stated. The bigger the sample size she chooses, the better. And she's going to ask these constituents if they support her or not. She can't ask all 72,000, that's why you'd need to do a sample. I'm going to come back to this warm-up question 2 later on as well. This is going to be one of the examples we're going to talk about this hypothesis testing for. Question 3. In a manufacturing process, the proportion P of faulty items has been found from long experience to be 0.1. In a sample of 100 items, calculate the probability that 8 are discovered to be faulty. Now you need to recall here, this is actually going to be a binomial distribution, because you can think of it, these items as being either faulty on one hand or not faulty on the other. And so if I call this distribution x, it will follow a binomial distribution with 100 trials. Each item can be considered a trial, and the probability of a fault being 0.1. So what we want here is to find the probability, P, that our distribution takes for precise value 8. So P, x equals 8. Now, just to remind you, this is a class whiz job, or can be. So we're going to press Menu, 7. We want a particular exact probability, so we go for binomial PD, option 4. Press 2 for variable. And we want 8 from 100, where the probability of this happening is 0.1. So they are the parameters. Press equals, and we get generated 0.115 to 3 significant figures. And so that's a probability of there being 8 faults from 100, assuming this binomial distribution. Lastly, Calculus Corner. This is going to be a new feature. Calculus deserves its own corner because it's such a crucial component in this A-level. So we need to find the integral of from 0 to 1 of root x plus the cube root of x dx. So let's just rewrite this out in terms of power form. X to the half is the same as the square root. That's my email just going there. And then the cube root of x, that's the same as x to the power of 1/3. So that's what we're going to be integrating with respect to x. Now recall, when we integrate, we increase the power by 1 and divide through by the new power. So increase half by 1, that becomes 3/2. Divide through by 3/2, that's the same as multiplying by 2/3. So what we'd have is 2/3 x to the 3/2. And similarly, for this one here, we're going to have 3/4 x to the 4/3 between the limits of 1 and 0. So if we input x being 1, this here becomes 2/3 plus 3/4, because 1 to the power 4/3, in fact 1 to the power anything, that's going to be just 1. So 3/4 times 1 is 3/4. Add those together, and oh, by the way, we can subtract 0 if you really want to, but hopefully you'll see that's not going to exactly do much. If we put 0 into this for x, it's going to make the whole thing equal to 0. So anyway, 2/3 plus 3/4, that gives you 17/12. And just to remind you how you can check this on a class whiz, you can use this integral button here. Let's go back to mode 1, sorry. Press the integral button and input the limits. So the lower limit is 0, upper limit is 1. And the function we wish to integrate is, first of all, root x, so square root symbol, alpha x, move along, then plus, then shift, cube root symbol, alpha x, to get this. Press equals, and you'll notice your calculator takes a bit of time to work this out, but eventually drops out with, the suspense is killing me. Wow, there we go. 1.4166667, which is not the best form to give the answer in because this is a decimal, but if you were to try 17 divided by 12, 17/12, which we've got here, that would give you this decimal answer. So that's one of the drawbacks of using the class whiz. It will give you a decimal answer, where with integrals and calculus generally, unless a question says otherwise, it's best to give you answers often in exact form. So let's move on to what we're talking about today. So what we're mentioning today is this idea of hypothesis testing. So before I get into the nitty-gritty of definitions, I'm going to try and give it to you in a simple way as I can. So I want you to imagine, first of all, that the whole point of hypothesis testing is to test out an assumption for a probability distribution by doing either an experiment or taking a sample. So, for example, one assumption we might have is that if you flipped a coin, you might well assume that the coin is fair. In fact, that would be an almost automatic assumption at your age of 16, 17, 18, probably. If you flip a coin, it's going to be fair. 50% heads, 50% tails. So your assumption could be that the coin's fair. The alternative, therefore, if it's not fair, it has to be biased. Let's just go with the idea here that, let's say it's biased towards heads. So how could you test if it's biased or not? Well, you could test this by carrying out an experiment. Let's say you've got loads of time in the world and you flipped it 100 times. You could then record the number of heads, couldn't you? So if you did that, then how many heads would it take you to change your mind from, well, I've got to say 55 heads, or I've got 60 heads. That's a bit unlikely, but it's not unheard of. That's just sort of natural chance. But how many heads would it take you to go, hold on a minute, this is absolutely freakish. Something must be wrong with our assumption. So it's a case of where do you draw that line? Would 70 heads out of 100 change your mind? Probably. If you got 90 heads out of 100, you'd damn well be thinking, if you had any sense, something's wrong with this coin. And so where you cut off between thinking, well, that's just natural chance, that's not too weird, and going over that line to thinking, this is absolutely nuts, something must be wrong. This is what hypothesis testing is trying to nail down in terms of drawing that distinction line between it just being, well, hey-ho, it is probability, versus this is too unlikely to just be coincidence, something must be wrong. So, yeah, in red, this is what I'm putting here. It's a formal study. It's formalising and pinning down how you can test such assumptions rigorously against alternative explanations if something's wrong with your assumption, and we use probability models for this. Now, in this course for year 12, we're just going to be doing hypothesis testing for the binomial distribution. So before we get started, make sure you're fully brushed up and au fait with the binomial probability distribution from previous lessons. So, going into a bit more formal definitions here. First of all, a population parameter, what does that mean? Well, a population parameter, it's a value that describes a characteristic of that particular population you're looking at. So common population parameters could be the population mean and the population standard deviation. But like I said, in this chapter, we're going to be looking at the particular parameter of a binomial distribution, and that parameter is the probability of that binomial distribution. A hypothesis, okay, that's just a fancy word for, it's a statement made about the value of a particular population parameter. So our hypotheses are going to be linked to the probability assumptions of our binomial distributions. So we can test the hypothesis by either experimenting, for example, flipping a coin, or taking a sample from a population, like warm-up question 2, where you were sampling the constituents from that candidate. The result of the experiment, or the statistic you can calculate from the sample, that's going to be called the test statistic. So in the terms of flipping the coin, the test statistic would probably be how many heads you get. And the population parameter would be, for example, the probability of landing on heads. So just taking those two different scenarios, flipping a coin and the sampling of constituents, let's take these two situations. So one requires an experiment and one requires a sample. Let's look at those. So the first case is a coin, flipping a coin. So given that any coin discussed in the context of probability is defined as being two-sided, either heads or tails, we can then think about questions like this. Is the coin fair or is it not? How would you define a fair coin? Well, surely if you're defining a fair coin, that'd be probability of heads equals probability of tails, which is 0.5. Now, how could we test to find out whether the coin is fair or not? Just think about now. Pause the video and think about this. How you define an experiment or create an experiment to test whether the coin is biased towards landing on heads or not. It's not too arduous, but have to think about it. Okay, I'm going to reveal what I would do and what I would suggest to test this hypothesis. What I'd suggest is we could flip the coin in a certain number of times, that's called trials, and record how many times we get heads. The more number of trials, the better. We could then compare the probability of obtaining that many heads, assuming the coin were fair. So the more freakish the number of heads we get, for example, if we got, say, 10 out of 10 heads or 9 out of 10, that would be a very low chance of that happening. So the lower the probability of observing what we observe, the more likely the coin will be to be biased. For example, if you've got 6 heads, that's not too unlikely. 7 heads, that's pretty unlikely. But if you were to get, say, 9 or 10 heads, you might well conclude the coin is likely to be biased and reject your assumption that it's fair. Case 2, an opinion poll, going back to warm-up question 2. So let's just say the selection candidate is thinking that she's got the support of 40% of her constituents, but she might be overestimating herself there. So she's wanting to get some peace of mind. Is that correct? Or maybe I'm less popular than what I think I am. So a researcher is hired by a local newspaper to find out whether her claim is accurate or not. How could this claim be tested? How could the researcher test this claim for her? This is essentially what we talked about in warm-up question 2, but with a bit more detail. So have a think about how you could test her claim, and then I'll reveal what I'd suggest we do. Okay, so I'm going to reveal it now. Let's see if your idea in your head or what you've got written down is similar to mine. So what I'd suggest here is a researcher could take an ideally large random sample of the constituents and ask them if they support this candidate. The number of people that support her, or the proportion of them, could then be recorded, and then the researcher can then calculate the probability of obtaining that value that she did get if 40% of all candidates did support her. So we can then calculate, assuming that she's right, the chance of the observed number of people supporting her actually happening. So for example, let's say she asked 100 people. Maybe 30 said yes. That might be a bit under what you should expect, but maybe she can put that down to just being unlucky. But if she only got, say, 10 people out of 100 supporting her, or 5, that would be a much lower chance of that happening if she was right in saying the probability was actually 40%. So the lower the number supporting her, the less likely that would be if she were right. So the lower the probability is of it happening, the more likely that her assumption would be incorrect. The more likely, for example, that she's overestimating her support. So let's have a look at this now. So now that we've designed the method for generating a test statistic in both cases, we need to form 2 hypotheses for each case. Okay, the default hypothesis is called a null hypothesis and is given the label H0. The null hypothesis is the default. It's the hypothesis that you assume to be correct. The alternative hypothesis, as you've highlighted in yellow, the alternative hypothesis H1 tells you about the parameter if your assumption is shown to be wrong. So using the coin flip example, the null hypothesis H0 is a probability of getting heads is 0.5. An alternative hypothesis, if it's biased towards being heads, is that the probability of heads may be greater than 0.5. So, like I've just said here, case 1, a coin, the null hypothesis H0 would be that the probability of head is 0.5. For the opinion poll, if we're assuming that her support is 40% of the population, then the null hypothesis would be that the probability or proportion of someone supporting her is 0.4. The alternative hypothesis for the coin, if it's biased towards head, is that the probability of heads is greater than 0.5, whereas for case 2, this opinion poll, it might be that she's actually overestimated her support. In that case, the probability of somebody supporting her may be less than 0.4. Hypothesis tests with alternative hypotheses in the form where the alternative hypothesis is the probability is less than or greater than. That's called a one-tailed test. The tailed bit here, where it says one-tailed, that's nothing to do with heads and tails, by the way. It means one-tailed in terms of we're only looking at one other aspect. So in one case here, we're looking at the probability being greater than 0.5, not greater than or less than. We're just looking at one way, just greater. Here we're looking at just less. The obvious alternative to this one is if it's two-tailed. So if it were two-tailed, that would be in the form where the alternative hypothesis is just saying the probability is not what we're assuming it to be. Now that's two-tailed because if we're just simply saying that the alternative hypothesis it's not equal to our assumed probability, the probability could either be lower, one tail, or higher, which should be the second tail. Whereas here, if it's just one tail, we're just looking at either lower or either higher. To carry out a hypothesis test, what we always do, we always assume that the null hypothesis is true. We always go off that assumption first. Then we consider how likely it is that the observed value of a test statistic was to occur if the null hypothesis were true. So if this likelihood is less than a given threshold, this is the cutoff I was mentioning earlier. If the likelihood is less than a given threshold, this is called the significance level of a test, by the way. then we reject the null hypothesis. So for example, if we wanted to test this coin hypothesis about it being biased towards head, let's say we tested at the 5% significance level. What that would mean is we would reject the null hypothesis if the chance of us getting a certain number of heads was only 5% likely. So if it were only, say, 5% likely or 4% likely, we could go with a 96% or 95% safe bet that our initial assumption is wrong. Now, of course, it could be that this freak event, let's say it was only 1% likely to happen, there is always a chance of wrongly rejecting the null hypothesis because anything can happen, for example, winning the lottery. But the idea of the significance level is we're fairly damn safe that the null hypothesis is going to be wrong. So the smaller the significance level we test at, the more safely we can say the null hypothesis is incorrect. So again, case 1 and case 2. So if the experiment is carried out to 5% significance level for the coin, what conditions would happen where the null hypothesis would be rejected? Okay, so for this case, if we let x be the test statistic, the expected number of heads, and little x be the actual number of observed heads that came out for any particular experiment, we'd reject h0 if the probability of a test statistics being equal to or more than that number of heads was less likely than 5%. That's when we would reject h0. We'd accept h0 if the chance of getting that many heads or greater was more than 5%. So although it may have been pretty unlikely, it wasn't that unlikely. We'd reject it if the chance of getting that many heads or more was really small, less than 5%. For case 2, this opinion poll, if we tested at 2% significance, we'd reject the null hypothesis, we'd accept the null hypothesis if the chance of this candidate having that many people supporting her or less was actually less than a 2% chance. So if y is a test statistic, the expected number of people supporting her, and little y is the actual number of constituents that supported her from the sample, we'd reject h0 if actually this number y was so small that the chance of the test statistic taking on the value of y or smaller is less than 2%. Then we'd say, with at least 98% certainty, actually yes, this candidate is overestimating her support. This will make more sense, please trust me here, it'll make more sense with some examples. That brings me on to this point here, an actual example, a coin. So let's imagine we've got this coin and we're going to say the test statistic x is going to be the number of heads that come up. And we're going to model this as binomial, 10 trials, p being the probability of landing on, probability of landing on heads. So given that 10 flips of the coin were carried out, let's say the coin, for example, landed on 7 heads out of 10 throws. So is that going to be unlikely enough to reject our assumption the coin is fair, or isn't it? This is what the whole idea of hypothesis testing is about. So this test, we're going to assume that the coin's fair. The alternate hypothesis is that the coin is biased towards heads. We're going to test at the 5% significance level. So below is a vertical line graph showing the probabilities for each number of heads obtained. So if the coin were fair, the chance of getting 0 heads out of 10 is so freakishly small, it doesn't even register as a line. The modal number of heads, or the most expected number, would obviously be 5. So that's a peak there, that's the most likely. 6 is unlikely, 7 is pretty unlikely, 8 very unlikely, 9 and 10 virtually no chance. And so is 7 going to be a critical point or not? So first of all, what I want you to do is to think about this table of values here. So use your calculator to complete the below table for the cumulative probabilities for this distribution. And we're going to round the values to 4 decimal places. And so this here is just going to be a revision of how to use the ClassWiz calculator for calculating cumulative binomial probabilities. So first of all, obviously, as I've just said, we need the ClassWiz calculator. I'll just remind you how to get onto the correct mode. We don't want the precise probabilities for any particular value, we want cumulative ones. And so we press Menu, 7 to get into statistics mode, and then scroll down till we see binomial CD and press this option here. Go for variable mode. List, unfortunately, doesn't round off correctly. So it's very good for an overview, but I've noticed it doesn't round off correctly. So go to variable. Now here, first we want to work out when x is 0, the chance of getting 0 heads out of a total of 10 possible trials. And we're assuming here that the null hypothesis is the probability of flipping a head is 0.5. So our first probability we get is 9.765, 6 times 10 to the minus 4. And so that is going to be 0.0009766. So we want to round it to 4 decimal places. So this 9 here is going to round up to 10. So we get 0, 0, 1, 0. So this first answer here, the probability that we achieve up to and including 0 heads is very low. It is 0.010. In a similar way, let's work out the cumulative probability that the number of heads is up to and including 1. In other words, that the number of heads rolled is either 0 or 1. So if we just press AC and go back and type in 1 instead of 0, press equals, we then get 0.0107. And so that gives us our next probability here. So pause the video. I want you to just work out, if you can, the next probabilities from 2 all the way up to and including 10. If nothing else, just to recap how to use your calculator to work out the binomial cumulative probabilities. Okay, so without further ado, here are the completed probabilities. Just check yours are the same as mine. And here they are. So the numbers are increasing all the way up to until we get to 1, when the probability, obviously, that the number of heads rolled is up to and including 10 includes every single possibility and outcome. That obviously gives you exactly 1. And so what I need to explain now is what's meant by the critical region. The critical region is the section of the distribution that would cause us to reject the null hypothesis. And so what we're wanting here is the region that's less than 5%. And so have a look here. We're looking at where this number here goes above 0.95. So it's tempting to think the critical region is 8, 9, and 10. However, if we just look here, where x is 8, what this means is, if we remember, this tells us the probability that x is up to and including 8, which is obviously 0.9893, that's the chance of everything minus the probability that x is 9 or greater. So that's obviously 0.9893. So therefore, the probability of x being 9 or greater is going to be 1 subtract 0.9893, which gives us 0.0107. And so this definitely is less than 5%. But what we need to do now is think about what's the probability of x being 8 or greater. Is that going to be less than 5%? So can we go one further and say that our critical region may include 8 as well? Well, the probability of x being greater than 8 or equal to 8 is equal to 1 minus a probability of x being up to and including 7. But we're told here the chance of it being up to and including 7 is 0.9453. If you use your calculator to work this out, that would give us 0.0547. Now that's actually just above 5%, so that's not yet below 5% significance. And so the chance of x being up to and including 8 isn't actually something we'd end up rejecting, because that's still above 0.05. So the first value which would cause us to reject the null hypothesis is this one here, where x is 9 or greater. So the critical region is where x is 9 or greater. So the critical region is this. When x is 9 or 10, that's when we'd end up rejecting H0. So another way we can think of this is as such. So we could think of this either as saying the critical region is x greater than 9, or we could just say x equals 9 or 10. So it says here to label the critical region on figure 1. So the critical region here is 9 or 10. Oops. Can't seem to write anymore, that's rather embarrassing. Never mind. So critical region. ITICAL region. Now, if something isn't in the critical region, the other region which causes us to accept H0, you might be able to guess, if it's not the critical region, it's going to be the acceptance region. And so everything else is where we wouldn't reject H0. And so from 0 through to 8 is where we wouldn't start thinking that the coin is biased towards heads. So this is called the acceptance region for H0. The critical value for x, well, the critical value I need to explain, is the first value which would cause us to reject H0. And so it's essentially where the acceptance region ends and the critical region begins. And so the first value inside the critical region, moving away from the acceptance region, is x equal to 9. And part D, state with reasoning whether or not H0 is rejected. Well, H0 is accepted. If we remember what we said earlier about how many heads were obtained, we said earlier that we had 7 heads which were obtained. So the number of heads obtained was 7, which is here, and 7 lies within the acceptance region. And so for our reasoning, we could either say 7 is less than 9, or we could just say that 7 is within the acceptance region. Or 7 is within the acceptance region. So either or explains nicely why we don't reject H0. So although getting 7 heads is pretty unlikely, it's not so freakishly unlikely that it would cause us to doubt if the coin is biased. We just put that down to slightly odd, but oh well, that could happen. Whereas if we got 9 heads out of 10, then that makes sense that we start probably raising our eyebrows and thinking, hold on a minute, this coin isn't right. Anything below 9 we might think is slightly weird, but wouldn't be quite enough for us to reject the notion that the coin is fair. Case 2 of the opinion poll example. So here we're calling the test statistic y because the coin was x, and so this person, the candidate, is either going to have people supporting her or people that aren't supporting her. So again, it's binomial. So here we're going to say that 20 people were surveyed, and so the first parameter in the binomial distribution is 20. Now the probability, assuming the null hypothesis, we're assuming the proportion of people supporting this candidate is 0.4. The alternative hypothesis is that P is less than 0.4, in other words, that she's overstating her level of support. And we want to test this at the 2% significance level. In other words, we want to be 98% sure that we're right in rejecting the null hypothesis. So, of the 20 people surveyed, we're going to say here that 3 people said that they supported the candidate. So let's compare this probability against what we'd expect to happen. So first of all, as ever, we assume H0 to be true. This would be the distribution we'd get if we had, say, 100 or 200 or a great number of different samples of 20. So very few, so few in fact it doesn't record on the vertical line graph, would be 0 or 1 people out of 20 supporting her. Sometimes 2 people, 3 people, 4 people, and the most common number of people you'd expect to be supporting her would be 8 people, because 0.4 is 2/5. 2/5 of 20 would be 8, and so the modal number of supporters you'd expect would be 8. Then less and less likely as we go up, down to virtually 0 when we go to 16 or higher. Not impossible, but very, very low chance. So let's have a look and get this modelled using our statistics. So first of all, use the calculator to complete the below table for the cumulative probabilities for this distribution, up to and including for y less than or equal to 10. Remember, we're looking at this lower tail here. We're wanting to see what this is here. So let's have a look at working out these probabilities on a calculator. And so what we have to do here is go back to the class whiz, menu 7, scroll down, press 1, press 2 for variable. Now we want the first one to be 0, n to be 20, and type in the probability as 0.4. So this first one is a number to the power -5. So this is just going to be 0.0000 to 4 decimal places. As you can see from here, next to nothing. So that first probability is just 0.0000. Let's try next when y is 1, what that probability is. So press AC, press 1. This one would be 0.0005. So going back here, we fill this one in. Try and fill the rest in yourself. Press pause now and do that if you can. Then press play and I'll show you what the other probabilities, cumulative probabilities, should have been. Okay, here are the rest of them. I'm hoping you got these as well. Now we need to think about what the critical region of this distribution is. The critical region is where we'd reject H0. So when the chance of y being up to and including little y is no more than 0.02. Remember, 2% significance. And so that's next to nothing. That's small. This is small, as is this. When we go to 4 or higher, that becomes over 0.02. And so the biggest number of supporters we could have where we'd still reject H0 would be 3. And so the critical region is where x is up to, sorry, y is up to and including 3. So this is the critical region, and again, like I said before, if it's not the critical region, it's the acceptance region. Up here is the acceptance region. The critical value is the first value as you move away from the acceptance region, which would cause you to reject H0. And so as you move from the acceptance region into the critical region, you can see the first value is 3. That's the critical value. So the critical value is when y equals 3. State with reasoning whether or not h0 is rejected. Well, if we just go back a second, we can see here from what we said before, we said 3 people supported the candidate. So 3 people supported the candidate, that's this value here, that is in the critical region, therefore we reject h0. And so h0 is rejected now you can say because 3 is in the critical region, or you can say something like because the probability that y is up to and including 3, as you can see here from the table, that probability is 0.0160, and that's less than our level of significance. In other words, it's less than 0.02. Part D, state the probability of y falling within the critical region. So this is this value here. So the chance of y falling in the critical region is a probability of y being 0, 1, 2, or 3. The probability of y being up to and including 3, which, as you can see from the table, is this value here. So that value is equal to 0.0160. So although we're after a 2% level of significance, it's very rare that level of significance actually exists. So this here is sometimes called the actual level of significance. So I'm going to explain this in a bit more detail now. Yeah, so from part D, case 2, I just showed you, that tells us the actual significance level of the test. And what this means, I've highlighted it in yellow because it's something we need to know about. The actual significance level is a probability of a test statistic falling within the critical region. It's the same thing as saying, but it's also the probability of incorrectly rejecting h0. So h0 could be rejected when h0 is still true. So in that example from before, there's a 1.6% probability that the candidate would have 0, 1, 2, or 3 people out of 20 supporting her, whereas actually the true proportion is 40%. That could happen, but it's just very unlikely. So just summarising this, case 1 and case 2. So case 1, the test was flipping a coin 10 times to determine if a coin is biased towards head. Our test statistic was the number of heads obtained. Hypotheses, h0, p equals 0.5, h1, p is greater than 0.5, where p equals probability of a coin landing on heads. The condition for rejecting HO and the conclusion from it, HO is rejected if the probability of our statistic being equal or greater than a particular number is less than 0.05, 7 heads were obtained, and that probability of the test statistic being 7, 8, 9, or 10 was 0.1719, which can be worked out from the tables by doing 1 minus the figures. That's about 17% chance, which is definitely bigger than 5%. In other words, 17%, although fairly unlikely, isn't that low, so we accept h0, the coin's probably okay. Whereas in case 2, we had a test which was sampling a population of constituents to determine whether a candidate was overestimating her support. Our test statistic for this one was the number of constituents supporting her. Our hypotheses, our h0, was the proportion of people supporting her was 0.4, with an alternate hypothesis that the probability or proportion of people supporting her was less than 0.4. And the condition for us rejecting h0 was if the probability of the test statistic being equal or less than the observed number was less than 2%. We had that 3 constituents out of 20 supported it, which isn't much at all. Would be a 0.016 chance of that, which is less than 0.02. Therefore, because that's less than 2%, we reject H0, it's much more likely that this alternative is actually true. So what you need to do now is to try these exercises to get your head around it. In time, it does become easy, but it's a bit of a thing to get into the concept of this hypothesis testing. So do try exercise 7a if you can do, please, or all the questions on that if you could do. Get back to me if there's any problems, email me if you need any help, and I'll get back as soon as I can. I'll see you next in the next video, and once again, as ever, thank you for listening. Thanks, bye.